Here are 7 quick proofs that x plus 1 over x is greater than or equal to 2 when x is positive. Proof 1, squaring the square root. Think of the quantity square root of x minus 1 over square root of x squared. Since this is the square of a real number, it must be positive, greater than or equal to 0. This quantity squared is x plus 1 over x minus 2, which is also positive. Adding 2 to both sides gives x plus 1 over x is greater than or equal to 2. Proof 2, check the discriminant. Set x plus 1 over x equal to a for some real number a. Multiplying by x and rearranging gives a quadratic equation, x squared minus ax plus 1 equals 0. The discriminant of this quadratic equation is a squared minus 4, which means that for this to be a positive quantity or 0, a must be greater than or equal to 2, which gives us directly that x plus 1 over x must be greater than or equal to 2. Proof 3. Find the minimum of a function using the derivative. Set f of x equal to x plus 1 over x. F prime of x is then equal to 1 minus 1 over x squared, and f double prime of x is equal to 2 over x cubed. We want to find when the first derivative is equal to 0, f prime of x is equal to 0 when x is equal to 1. If we check the second derivative at x equals 1, f double prime of 1 is a positive number, which means that x equals 1 is a minimum. F of 1 equals 2, which means that f of x must be greater than or equal to 2, which means that x plus 1 over x is greater than or equal to 2. Proof 4, the AMGM inequality. According to the AMGM inequality, a plus b over 2 is greater than or equal to the square root of ab for positive real numbers a and b. Let a equal x and b equal 1 over x. This gives us x plus 1 over x divided by 2 is greater than or equal to the square root of x times 1 over x. But the square root of x times 1 over x is equal to 1. And this gives us, after we multiply by 2, directly that x plus 1 over x is greater than or equal to 2. Proof 5. Taylor series for the exponential function. Set x equal to e to the t, where t is a real number. We then have x plus 1 over x equals e to the t plus e to the negative t. The Taylor series expansion for e to the t plus e to the negative t is 2 plus 2t squared over 2 factorial plus 2t to the fourth over 4 factorial plus so on and so on and so on. Notice that all the powers of t are even. This means that every quantity is a positive number in this expression, which means that it is definitely greater than or equal to 2, which gives us that x plus 1 over x is greater than or equal to 2. Proof 6, using a standard log inequality. It is known in inequality that u minus 1 is greater than or equal to ln u. If we set u equal to x, then that means that x minus 1 is greater than or equal to ln x. If we then set u equal to 1 over x, this means that 1 over x minus 1 is greater than or equal to ln of 1 over x, but ln of 1 over x is equal to negative ln of x. If we then add these two equations, that gives us that x plus 1 over x minus 2 is greater than or equal to 0. Adding 2 to both sides then gives us x plus 1 over x is greater than or equal to 0. Proof 7, overkill integration. Let f of t equal the quantity e to the negative t minus e to the negative xt squared. Here x is some positive number, and in this expression we regard as a constant. We notice since this is some real number squared, then f of t is always greater than or equal to 0 for all values of t. This means the integral from 0 to infinity of f of t dt must be positive. But if we integrate, the integral of f of t dt is from 0 to infinity is 1/2 minus 2 over x plus 1 plus 1 over 2x. This quantity must be greater than or equal to 0, as we said before. If we then multiply both sides by 2x plus 2, which is always positive, so we maintain the direction of the inequality, we then get x plus 1 minus 4 plus x plus 1 over x, which equals x plus 1 over x minus 2, is greater than 0. Once again, we add 2 to both sides to get x plus 1 over x is greater than or equal to 2.